In this module, we will consider the idea of a two-force body. So a two-force body is as simple as it sounds. It's a body that has two forces acting upon it and nothing else. So here is a schematic of a body with two forces called F1 and F2. In the next few slides, we're going to apply the laws of equilibrium to see that we cannot just put the forces anywhere, but they have to obey certain rules. And maybe you can already see something wrong with this picture, why if I tried to have just those two forces, that would not work out for a statically equilibrated situation. Can you think about that? So suppose we first apply the idea that if the body is in equilibrium, the sum of the forces on that body must be equal to 0, which means in this case the vector F1 plus the vector F2 equals the 0 vector. Another way to say that is the force F1 is the negative of the force F2. So the only way that the sum of two forces can be 0 is if the two forces are opposite of each other, which means they have the same magnitude but opposite direction. So we cannot have this situation. Rather, we must at least have this situation, where the two forces are now parallel, opposite direction, and one is exactly the negative of the other. Now, having said that, we're still not done, because there's another condition of equilibrium, which is that the sum of the moments about any point must be 0. So let's choose a point P. Let's say that point P is on the line of action of F1. And I now say, let's sum the moments about the point P. What we see is that the vector F1 goes through the point P and doesn't make a moment about point P, but the vector F2 does not go through the point P, and therefore it would make a moment, but the sum of the moment has to be 0. So the only way to get 0 is if F2 also goes through the point P. So it's not this situation, it's this situation. Now what we see is that in a two-force body, not only are the forces equal and opposite, they are also on the same line of action. Okay, that's our summary. The two forces are equal in magnitude, opposite in direction, and they lie on the same line of action. And I'll note here in this diagram, I'm now using the scalar symbol, using an F scalar to denote the magnitude of each vector. So we really have seen this already, although we have not used that terminology. Remember our first couple of weeks of the class and we studied basic free body diagrams like a section of a cable or a section of a bar. Those were two-force bodies because the forces were aligned along the axis of the bar and one was the opposite of the other. Can you go back to module 2.3 and see if there's any other things that you can also think of that might have been two-force bodies? We also just, in our previous module, saw tables of reactions, and here we see both straight and curved objects, but again, the key here is those objects are attached only at their endpoints, so that would count as a two-force body. Each end is where one force is contacting that connecting element, and we saw that our schematic of the reaction is that those bodies, like the cable or the link, can only exert a force either parallel to themselves or through the line of action of the two endpoints. And notice that this means that these objects give you only one independent unknown reaction. Note that the angle theta is considered given, so theta is not unknown, only the magnitude of the force. So let's do an example. Here's a curved bar. Let's say I think there's a force F acting at point B in some general direction, and at point A I have the body anchored by a pin or a hinge. Now maybe you don't see anything wrong with this initially, but our theory already tells us that if you were to draw that body's free body diagram, the force at point B cannot be in any direction. The force in point B has to go through point A, and whatever force is at point A, then also goes through point B. Now, think about this. On one hand, this makes sense because we've also just talked about in our table of reactions, we see something called a curved link. And the curved link table tells us just put one force along the line of the two endpoints. But you might ask yourself, hey, I thought point A, we were told it was a hinge. And I thought that if I go to the same table and look up a pin or a hinge, the table tells me to give me two forces, Rx and Ry. So the question is, are these contradicting each other? Well, let's look at this a bit more closely. Suppose I were to look at the force F at point A and draw its two components. And then let's suppose I draw a horizontal line and use that as a reference to get the angle alpha of the two endpoints of the line AB. And because we've done a lot of trigonometry, I think it's clear that the two components of F are now force F cosine of alpha and F sine alpha, which means we can see a direct correspondence. The AX force in the right-hand diagram is really F cosine of alpha, and the AY force is really F sine alpha. And because, again, we're considering alpha to be a known angle, this body has just one independent unknown reaction F. The AX and AY both depend on the same value of F, so they really count just as one, not two different unknowns. Now, let's go back to the beginning. Suppose you're still not quite believing all this and say, well, I'm going to put my force at B in whatever direction I want to go, okay? Let's now think about how we would study this if we didn't now talk about the theory of two force bodies, okay? You might also say, let's draw AX and AY at point A because it's a hinge. Let's now apply equilibrium. The first thing you would do is you'd say, write the sum of the force in X and Y, and it's clear in the X direction I have AX minus F cosine alpha equals 0, and in the Y direction I have AY minus F sine alpha equals 0. That's an easily solved set of equations for AX and AY. And then I say, let's take the moments about the point A. Now, because AX and AY go through the point A, they don't make a moment about A. If I then put in the perpendicular distance between point A and the line of action of F, I now see that the total sum of the moment about A is just from the force F times D perpendicular. But that cannot be 0 unless F is 0, and that wouldn't be a really interesting case, because if there's nothing happening, then there's nothing to do. So assuming that F is not 0, the only way that equation can be true is if F passes through the point A. In other words, if the angle alpha makes F go through the point A. So let's go back to that case. We cannot avoid this. The force at the point B must go through that endpoint at point A. The two force equations still give me the same result, and now I'll just write them explicitly. AX equals F cosine of alpha, and AY equals F sine of alpha. I'll put that right on the diagram. And now, because the force at B is going through A, it automatically satisfies the moment about A equation. Okay, so where do we go from here? Let's take that force, or the two forces at point A, and make a force triangle as if it were two components of a given force. And I think it's clear, but just to go through this, if I took F cosine alpha squared plus F sine alpha squared, I get F squared. And if I take the square root, I see the magnitude of that hypotenuse of that triangle is F, which means that the total equivalent force at point A really was, as we said before, a single force directed through point B with a magnitude of F. And so here we are at our original result that the two force body theory tells us. So in summary, we don't have to do anything. We are only doing these calculations now to demonstrate it, but the whole point of the two force body theory is so that you do not need to do these calculations. You can just simply assume that the diagram of the body looks like it does here. Two forces, equal magnitude, opposite direction, and on the same line of action. Couple of cautionary points. Sometimes a body looks like a two force body, but it really isn't. Suppose I look at this arm in the crane, CDF. Can you see why that is not a two-force body? I'll give you a hint. Imagine you isolate that arm away from the rest of the structure. Can you see now why that is not a two-force body? And in the right-hand object, I have A and B. You might say, wait a minute, that is a two-force body because I see only 2 points where something is touching it. There's 1 point of contact at A, 1 point of contact at B. Isn't that a two-force body? Think a bit more carefully about what reaction type you see at point A, and that might give you a clue.